In this video, I'm going to go through topic 5 of Edexcel P2 Physics. This is about nuclear fission and fusion. That's the main part of this topic, and also a bit about radioactivity in there as well. So let's start with isotopes. By the way, in this video I'll be going through the graded assessment sheets. I'll show you what I mean by that. That's this one here. I'll go through that at the end of this video. So all atoms, so isotopes, right? All atoms of oxygen, they have 8 protons. If it's an isotope, it will have the same number of protons but a different number of neutrons. So all atoms of lithium, they have 3 protons. Carbon, 6 protons. So all atoms of a particular element will have the same number of protons. In other words, they'll have the same atomic number. If they are a different isotope, they have the same number of protons, but they have a different number of neutrons. So that means they have the same proton number, the same atomic number, but they have a different mass number or a different nucleon number. So that means they have a different number of protons and neutrons. Okay, so it's just the number of neutrons that's actually changing the atom. So for an example here, you've got hydrogen, numbers 1 and 1, mass number 1, atomic number 1, so mass number over here, atomic number over here, both 1. Here's a different isotope of hydrogen, 2 and 1. It's still only got 1 proton. To get 2 at the top, it must have 1 neutron now as well. Over here, that must have 2 neutrons because it's still only got 1 proton. Still hydrogen, just got 2 extra neutrons. So that's isotopes. Some isotopes are radioisotopes, they're radioactive. Okay, so they give out radioactivity to try to become more stable. If you're doing triple physics, you'd learn about this with the NZ curve. So if an atom loses or gains electrons, it becomes a charged particle. We have names for these, they're called ions. Ions have an overall charge because the number of protons does not equal the number of electrons. Atoms have no overall charge because the number of protons is equal to the number of electrons, and we know that protons and electrons have opposite charges. Okay, if there are more electrons, than protons in an then the ion is negative. So more electrons than protons is negative. Fewer electrons than protons, so in other words, more protons, the ion is positive. And that's all you need to know about isotopes and ions. So you think about charge, go back to charge. Gaining electrons, you become negative. Losing electrons, you become positive. Right, so let's have a quick talk about radioactivity. So we've got a bit about radioactivity here. Please, I would suggest drawing this out as a table. I wrote this in as notes like this for people to read through a lot easier, and so people don't sort of just skim it because the table are quick information is taken in quickly. Actually read through it and then create a table out of this. So remember, radioactive particles are released from radioisotopes. 3 types of radiation, alpha, beta and gamma. They're all ionizing, and they're released in a random process from unstable nuclei. So radioactivity comes from unstable nuclei and it's random. Okay, it's completely unpredictable. So let's have a look at these. I will do a table. The first heading I would have is type of radiation. Then I would have what it's made up of. Then I would have charge. Then I would have mass. Then I would have ionization. And then I'd have penetration. So to go through those again, I'd have type of radiation. I'd have what is it, or what is it actually made up of. I'd have charge, mass, ionization, and penetration. So alpha radiation, it's a helium nucleus, 2 protons, 2 neutrons. Can't get through 5 centimeters of air or a thin sheet of paper. It's highly ionizing, positive charge. There's a mass of 4, 2 protons, 2 neutrons. Charge of +2, positive, 2 because of 2 protons. And its penetration is it gets absorbed by paper or a few centimeters of air. Beta radiation, that's a high energy electron from the nucleus, because what actually happens is a neutron becomes a proton and an electron. There's an electron that actually comes from the nucleus. Can't get through aluminium, so it gets absorbed by aluminium. So it's moderately penetrating, and it's also moderately ionizing, and has a -1 charge and a mass of this that's the same as an electron. So that's 1/2000 or 0. Gamma radiation, okay, is an electromagnetic wave, no mass, no charge, highly penetrating, not so ionizing, least ionizing, weakly ionizing out of all of these, and that's because it has no charge. You can reduce it, you can absorb some of it by using several meters of lead or concrete. Okay, that's the basics of radioactivity that you need to know. Remember that alpha radiation is a helium nucleus, so it has the numbers 4 and 2. So you could put 4 above alpha and 2 below, so it's 4 for a mass number, 2 for atomic number. Beta radiation has a mass number of 0 and an atomic number of -1 because of the fact a proton is created as part of this process. So, fission is the process of splitting atoms to release energy. So you're taking larger nuclei and making smaller nuclei and releasing energy from it. Two fissionable fuels are uranium and plutonium. So for fission to occur, the nucleus must absorb a neutron. So if it absorbs a neutron, the nucleus splits into two nuclei that are smaller. It gives out 2 or 3 more neutrons, and large amounts of energy are released. These extra neutrons that are released, so these extra neutrons that are released here, they go on and split further nuclei, which causes more reactions to take place. So that's how more energy is released. This is called a chain reaction. One neutron comes in, splits apart so it gets absorbed, splits apart the nuclei to 2, the single nuclei to 2 nuclei, and then the extra neutrons released go on and split further nuclei. So we need to be able to control this reaction, so we do it inside of a nuclear reactor. Here's a diagram of a reactor. So you have a heat exchange here. The heat released by the reaction turns the cold water to hot water, turns out to steam, steam turns to turbine, which turns a generator, which makes electricity. There's two things in a nuclear reactor that help to control the reaction, and that's the moderators and the control rods. The moderators slow down the speed of a neutron, more likely to be absorbed, and therefore more reactions will take place. Control rods absorb neutrons, so they can be used to alter the rate of the chain reactions, or you can stop the whole chain reaction altogether if you drop the control rods. So the control rods here are either lowered or raised to control the rate of reaction. Remember, the products of fission are radioactive, so these nuclei, these daughter nuclei, these waste products here that are produced, they're radioactive. So storage of that is an issue. And even to this day, we don't have a perfect answer, but we'll come up to that in a bit. You probably have covered it in lessons. I mean, the big issue is we don't really know how to store radioactive waste because it's such a long-term problem. There's a bit about it later on. We'll cover it when we talk about dangers of radiation in the next topic. We've probably covered it in lessons. But there's intermediate waste, which lasts a significant amount of time, but there's high-level waste, which lasts for a long amount of time. And they're the things we're really, really worried about. Nuclear fusion. So that's making larger nuclei from smaller nuclei. So think of it like Lego, sticking 2 Lego bricks together to make a big one. That's what fusion is. This also releases a large amount of energy, but the key thing about this is it makes no waste products. Okay, it's the energy source for stars. And the key difference between fusion and fission is smaller nuclei making a larger nuclei, fission is larger nuclei split to make smaller nuclei. Please don't mix those two up. So fusion is joining, fission is splitting. High temperatures and pressures are required for fusion. This is to overcome the idea of electrostatic repulsion. So what's actually happening is the particles in the nucleus, the 2 protons, they're actually, I'll show you what I mean. I've got some picture of the proton right at the top of there. The protons in the nuclei, there we go. So the protons in the nuclei over here, they're trying to repel each other. So these 2 protons are trying to repel 2 protons that are being shoved into it. They're trying to repel each other. So in fusion, what happens is you need high temperatures and high pressures to actually be able to overcome that. So large pressures and temperatures are required to overcome electrostatic repulsion. That's a real key sentence to understand, because we're trying to force 2 nuclei together. That there generally gains you 1 or 2 marks in the exam whenever they ask about why large pressures are required or large temperatures are required, or what are the conditions for fusion. So make sure you understand the conditions for fusion: high pressure, high temperature to overcome electrostatic repulsion. Cold fusion. So a very small part of the topic. Cold fusion was an idea put forward by 2 scientists called Stanley Pons and Martin Fleischmann. Whenever they ask about questions about this, it's generally about the issues about the validity of scientific evidence rather than this experiment itself. So you don't need to know much about the experiment that Pons and Fleischmann did. The key thing is that they thought that they actually found cold fusion. So in other words, being able to do fusion on Earth. They didn't. The experiment was not able to be replicated, so it could not be peer reviewed. So the area of science that I'll ask about for the exams in this bit is about peer review. So remember, any new scientific discovery should be peer reviewed. What we mean by that is that it should be checked by other people of the same level, so in other words other scientists, and they should check that the experiment can be conducted in their laboratory under the same conditions without any external factors affecting the experiment. If you can't replicate the results, it's not a reliable experiment. If it's not able to be peer reviewed, it won't be accepted by the scientific community. So the scientific community only accept ideas that have been peer reviewed, normally via a journal, which is like a scientific magazine, but more high level, or checked by the scientists. Right, so let's just quickly go through the assessment sheet for this topic. So describe when an atom becomes an ion. So that's gaining or losing electrons. Remember to say that gaining is if you gain an electron, they become negative. If you lose an electron, they become positive. Define the following terms: so mass number, protons and neutrons, number of protons and neutrons, atomic number, number of protons. State the composition of alpha, beta, and gamma radiation. So that's 2 protons, 2 neutrons. It's a beta particle. Sorry, it's 2 protons, 2 neutrons. That's an alpha particle. It's also a helium nucleus. A beta particle is a high energy electron, generally from the nucleus. Although it says define or state the composition, so you don't need to say from the nucleus, but get into the habit of saying it's a high energy electron from the nucleus. Gamma radiation, electromagnetic wave. State what we mean by an isotope and give an example. So think about the hydrogen example that we had at the start. Show what I mean. This one over here. Same number of protons, different number of neutrons. Another good example is carbon 12 and carbon 14. Compare the ionizing ability and penetration power of alpha, beta, and gamma. So the more ionizing, the less penetrating. So alpha is highly ionizing because there's a high charge, but it can't get through very much. It can't get through air, it can't get through paper. Beta, moderate on both. Gamma, not very ionizing. Okay, it's a 0 charge, but it's massively penetrating. Can go through many things. Compare and contrast the process of fission and fusion. It's a common question they like to ask. So remember to talk about the fact that fission is splitting while fusion is joining, and that fission makes waste while fusion doesn't. But also remember to include that they both create energy, and they both can be used to make electricity, and they both release large amounts of energy. They both involve the nucleus of an atom as well. Draw a diagram showing the process of nuclear fission and explain how the chain reaction occurs. So that's this idea over here. So a neutron coming in, splitting apart the nucleus, and that those neutrons then going in, hitting a further nuclei. Explain how a controlled fission reactor works. So that's this idea over here, explaining what's going on as part of this process, and explain why it's extremely difficult to make a nuclear fusion reactor. Okay, so remember the fact that fusion is difficult because it needs a large pressure and large temperatures. That causes containment issues, and it needs a lot of energy to actually make that happen. So it's difficult to replicate. And that ends our video on Edexcel topic 5 of P2 Fusion and Fission.